coming back from lunch. It's always an achievement. I want to say that this is a special talk. Within the workshop here at Simons, we have a historical crypto paper seminar series, and we try to visit historical papers and see what led to them, what they had in them, and how they've impacted things later. And one of the talks that we chose for this series, which is being organized by Vinod and Daniele, is to look into lattice crypto, and it was a perfect opportunity to choose Daniele to give this talk. So I'm happy that he agreed. So just to introduce Daniele a little bit, he did his PhD at MIT and is currently a professor at UCSD. And he's an expert in many, many things. Most people are narrow, but Daniele is really very broad. Logic, crypto, protocols, and in lattices specifically, he touches everything. Many of the basic primitives that we saw in the talks over the morning sessions were introduced by him. And he has the results on NP hardness of lattices, worst case to average connections, and various algorithms in lattices. He also introduced the rigorous analysis of ideal lattice-based crypto, expanding on the work which had appeared by NTRU. And he also contributed to our knowledge by writing books and lecture notes, which is usually a lot of effort and really a big contribution to the community. He also recently created a logic, introduced an algebra for reasoning about multi-party computation, something very forward-looking and maybe perhaps a bit before its time yet. Hopefully the time will come. He has served on in many leadership roles, chair of TCC, journals, and so on. He has won the McAtee Award for Best Student Paper, an NSF Career Award, a Sloan Fellowship, a Hellman Fellowship. And I have two things to say that are a bit less formal. First of all, he's really cool. He dances salsa, and he surfs, which is, I find really impressive. And I have to tell you that in his young days, he also rode a motorbike. That still is true. Oh my God! I put it out. Still young. Still young. That is true. Sorry for that. And the second thing that I wanted to say is sort of a story which I found amusing, which Daniele himself told me, of how you get into certain areas in research sometimes. So at MIT, maybe it's a good practice. They have this exam relatively early in your career where you have to read a paper and do some original research related to that paper. And Shafi, in her great wisdom, gave Daniele the ITICE paper on lattices. And that is how this whole thing started. So a great advisor with a great student, you really get fantastic things. So please help me welcome Daniele.
Okay, thank you, Tal, for the introduction, and thank you, Vinod and Daniel, for inviting me to give this historical talk on lattices. So, historical talk on lattices. Wow, I mean, that's quite something. I think it says quite a bit about how much this area is accomplished. I started, as you just heard, working on lattices in the early days of when lattices started being used to design cryptographic functions. And I pretty much worked in that area since then. So that's great that we got to a point where we give historical talks about it. This also says a little bit about my age. That's not as good, but yeah, that's the price for it. But I still ride a motorcycle, a different one, but yes. So, well, as you know, I'll be talking about lattices, and more specifically lattice cryptography. And well, lattices, you already saw them a number of times during the boot camp earlier this morning. I just have a picture there. I will not be much very technical in this talk. So this was just to put a picture there. And okay, so this is a lattice. You have a set of points in space that are arranged regularly. One relevant feature of lattices is that these are points in real space, in Euclidean space. So these lattices are mathematical objects that mix together some continuous and discrete properties. They are described by real numbers, but it is a discrete set of points in the topological sense that these points are far apart from each other. And we'll see how these come up in the study of lattice cryptography. Now, any historical talk about lattices, at least in the context of computer science, necessarily has to start with a mention of the LLL algorithm, given in the paper of Lenstra and Lovash, factoring polynomials with rational coefficients. So that was the application, but the paper is mostly known for this tool, this approximation algorithm that can be used to efficiently find solutions, approximate solutions to lattice problems. And the approximation factor grows exponentially with the dimension of the lattice, but the algorithm performs pretty well in practice, and it has been very, very useful in cryptanalysis. Now, that's not what I will be talking about. What I'll be talking about is what happened starting in 1996, when ITI came up with a paper generating hard instances of lattice problems that was really a turning point for lattice cryptography. And it marks the beginning of the modern use of lattices in the construction of cryptographic functions. So notice the difference. Up to this point, lattices were used mostly as a destructive tool, as a tool to break cryptography, to attack both crypto systems that were directly related to lattices, and also crypto systems that had nothing to do with lattices. There are attacks to various forms of RSA, which are based on lattice reduction. And only starting in 96, we started seeing a different kind of use of lattices in the construction of cryptographic functions. So that's not entirely true, and I will talk a little bit about that, but I will use this as the starting point. So let me start with a few quotes from this paper of ITI. So this slide doesn't have any picture, so just like the paper, and which is good and bad. Okay, so is you know, some a picture is worth 1,000 words, but some words can be worth 1,001 pictures. And I'll go back to this point at some later in the talk. So in this paper, I think it's a very nice, very good reading. So if any of you didn't read it because you know, there's so much to read, so better to read the most recent work. Yeah, you may want to go and yeah, take a look. It's not as scary as it looks. So in the paper, beside the technical results, he argued about the importance of the problem. Now, in cryptography, cryptography involves the generation of instances, hard instances of problems in NP, typically together with a solution. And you want to generate instances that are thought to be difficult. Now, we don't know, based on our knowledge of complexity theory, how to prove that something is difficult, that something requires a lot of time, at least if you stay within NP. So in order to find these hard problems, one typically resorts to one of two possible methods. One is to tap into computational complexity and the theory of NP-hard problems. Now, NP-hard problems, NP-complete problems are problems that are as hard as any other problem in the same class. So if any problem in NP is hard, then that problem is hard. So you found it. Or alternatively, you can pick a famous question that has been studied for a long time by mathematicians. The typical example is factoring. So we believe that factoring is hard, at least classically. And that's evidence that there is some hardness there. However, difficult to solve in both cases means difficult in the worst case. So that means that there is no algorithm that solves the problem for every possible instance. There is no algorithm that can be put there as an algorithmic solution to the problem. And the impact on cryptographic applications is that this gives no guidance about how to create hard instances of the problem. So a possible solution, it has long been realized that a possible solution to this issue is to find a set of random instances of the problems and then prove that if you can solve these random instances with some positive probability, then you can solve the hard, the famous mathematical problem in the worst case. And this gives you a way to pick the random instances. You can pick them according to this distribution, and you will know that they are as hard as solving the famous question. And that's exactly what Itai's paper did. Now, this is a very important result beyond lattices. So he used lattices as a tool to achieve this result in that paper, but he could have used any other problem, and lattices is simply what did a job for him. So there is a question that comes up pretty often. I saw this question asked many times during talks about lattice cryptography. A question that is typically dismissed by the speaker. Oh yes, there is an answer, I know the answer, but I will not answer it now because I want to talk about my work, and that question is not about my work. And the question is, don't we already have something like that already in cryptography? For example, the discrete logarithm problem is random self-reducible. So in the discrete log problem, more specifically, let's consider this version. So you are given a prime number P that defines a multiplicative group, ZP star, and also a generator of the entire group, or sometimes a prime order subgroup of ZP star. And the input is an element of the group G generated by this element. And the question is recover I, recover the exponent of this element. Now, this problem is random self-reducible in the sense that if you can solve this problem at random with some positive, even a very small probability, but some non-negligible positive probability, when G and H are chosen at random, then you can solve the problem also in the worst case. Now, in the previous slide, I described how you can have this kind of relation to find hard instances. The two problems don't have to be the same. In the case of discrete log, they happen to be the same problem that you can solve on the average or solve in the worst case, and that's why it's called random self-reducibility. The proof is pretty simple. You probably saw it before, or you figured it out as I was presenting the description of the problem. So if you are given an arbitrary worst-case instance of the problem specified by G and H, what you do is to raise these two group elements to a random power, G to the A and H to the A and B. So you multiply it, you multiply A and B together. Notice these G prime and H prime are almost uniformly distributed. So they describe a random instance of the problem. Even if you fix G and H and then you choose A and B at random, G prime and H prime are random. So if you can solve this problem with some probability, then you will find a solution to this problem, which is the exponent of G prime of H prime with respect to the generator G prime, which is I times B. And once you do that, you can recover I, that is the solution to the original problem, just dividing this number by B. So what does this mean? So this means that we know how to pick G and H in the discrete log problem. We know that the right way to pick G and H to make the problem hard is to choose them at random. However, this proof does not give any guidance about how to choose the group G. Now, I'll talk about lattices at length, but before we get to lattices, let me talk a little bit more about this discrete log problem, because I think that the contrast with lattices illustrates some important points about lattice cryptography, and some of these points are also quite relevant in the context of some more recent developments of uses of lattices. So what is the difference between these two kind of hardness? Now, in the lattice case, the assumption is that there is no algorithm that can solve lattice problems efficiently, or equivalently, the complexity of solving lattice problems grows exponentially, or at least super polynomially in the dimension of the lattice, n. So we don't really have a single distribution on problems. We have a set of distributions, one for every value of n. So you may think that the situation with discrete log is not much different. You also have a set of distributions, one for every group, and the conjecture is that the complexity of solving this problem grows super polynomially in the bit size of the modulus or the group size. Now, this is not quite the same as what we have for lattices, and the reason is that for every n, you can think of n as a security parameter, there are exponentially many primes p. So when you make a conjecture of this form, what you are asserting is that so typically this prime p is chosen at random. You set the value of n, the security parameter, and then you choose the modulus as a random prime for that length. And the assumption is still an average case assumption. We are assuming that when the prime p is chosen at random, then the problem is hard to solve. And if you phrase this in the context of complexity theory, so if you were to assume that when you pick this prime p at random, then you get a hard p with some positive probability, say epsilon, that's what is called a weak one-way function. Now, you can make a stronger assumption and ask that when you choose p at random, then you will get a hard p with probability that is exponentially close to 1, and that would be a strong one-way function. When you make an assumption of this form, you are making a super strong assumption. You are saying that if you pick p at random, then it will be hard with probability 1. So that's very, very strong. It is even stronger than what you typically assume in the average case setting. And so the issue is that we do not know how to relate the complexity of the discrete log problems in different groups for different primes p. So the random self-reducibility does not give any guidance about the choice of the group. Now, you could try to fix this problem, for example, by just picking a prime. Let's say that for every value of n, instead of picking a random prime of length n, you choose the first prime of length n. And we know there is always at least a prime between 2 to the n and 2 to the n plus 1, and you could define Pn to be the smallest. Let's not worry about how to find it. Now, so that's fine. You get something which is closer to the situation that we have with lattices, but it's clear that we are getting there with something that is very ad hoc. There is a part of the definition of this problem which is very kind of arbitrary. Why take the first one? Maybe the first one is easy, and I mean, there's no reason to believe the first one would be easy, but it's clear that it is kind of a cheat. So now there is more than that. So in the case of lattices, if you consider this sequence of problems in increasing dimension, we also know that you can reduce lattice problems in dimension n to lattice problems in a larger dimension. The way you do it is just by adding some dummy coordinates and just putting some big numbers there. So in a technical sense, solving lattice problems in larger dimension is at least as hard as solving lattice problems in lower dimension. And you can think of these sequences of distributions in larger and larger dimension as a single problem for which you consider subsets of growing size. So in a sense, yes, we have a single problem which is assumed to be hard in the worst case, and there is really no randomness or no uniformity in the assumption. And no such reduction is known for discrete log. So even if we take this very specific example, is there any way to show that to reduce discrete log with n-bit prime modulus to discrete log in a prime modulus with larger bit size? And one last issue is that this discrete log problem, I mean, the hardness of the problem seems to depend on the representation of your numbers. And the group, the multiplicative group of numbers modulo P, we know is isomorphic to the additive group of the numbers modulo P minus 1. But the discrete log problem in this group is trivial. So the fact that the problem is hard somehow depends on how the problem is represented. Now, you can always make a problem easy by choosing some weird representation that implicitly contains the solution to the problem. So it's not really a formal argument, but here, I mean, there's no doubt that it's a natural representation of the elements of the group. And yeah, I'm not exactly sure about what it says about the problem, but for lattices, I don't know any reasonable representation of lattice problems that makes them easy. And also, I talked about discrete log with modulo prime. You can also consider other groups. For example, discrete log modulo the product of two primes. You can take two random primes of the same length. And so which of these two families should you use? So let me ask you a question. I mean, prime, that's what you typically use. That's probably the most sensible choice for many applications. But consider the following question. Assume that somehow, for these two distributions, discrete log modulo prime or discrete log modulo prime product, say one of them is polynomial time solvable, the other one is hard. Which one would you pick? Well, Ron has good reasons, independent reasons, to prefer one of the two distributions. It's the RSA group. But yes, personal preference aside. So the question is, if the discrete log problem, so consider the discrete log problem over modulo prime or modulo the product of two primes. So modulo prime or in an RSA group. Okay? If, so we don't know, there is no strong mathematical evidence that one class of groups is better than the other than the best known attacks. So maybe one of them is easy. So let's say that somehow one of them is easy, polynomial time solvable, the other one is hard. Okay? So I tell you that. Okay?
Some particular
No, for random P and Q, for random P and Q.
You asked us to guess which is the case.
Hmm? Which one would you go? So I'm making this point that the random self-reducibility does not provide any guidance about the choice of the group, and I'm trying to trick you into giving the wrong answer. So whatever answer you have in mind, give the other one, okay? But this may be part of the trick. Okay, anybody wants to take a... Huh? They're both easy? I think it could be the case that one of them is hard, one of them is wrong. So I think that could be the case. And, well, if you didn't see it yet, the reason is the Chinese remainder theorem. So you know that Z modulo PQ is isomorphic to the product ZP times ZQ, assuming that P and Q are two different primes. And so this essentially tells you that ZP is a subset of ZPQ. You can embed the ZP inside ZQ. And this gives you pretty much a reduction from the discrete log modulo P to the discrete log modulo PQ. So that's a reduction that says that if you can solve the problem modulo PQ, then you can also solve it modulo P. Okay? So technically, so if I give you this instance to be solved, what you do is to pick another random prime of the same size, and then you turn this problem into the other one, adding a dummy coordinate. So if one of them is polynomial time solvable and the other one is not, we know that this one is the hard one and that the other one is easy. I mean, there is no other possibility. And it's not clear how to give a reduction in the other direction unless you know the factorization of the modulus. If you know how to factor the modulus, then yeah, you can break discrete log into the two components.
Discrete log in a composite order.
Yes, I expected this question. But so if you can take the discrete log modulo PQ, then you can factor PQ. If you can take the discrete log modulo prime,
you can factor P.
You can still you can factor P. So yeah, it's yeah. So I didn't look into this deeply, so you may be able to find a way to prove the equivalence between the two problems. But yeah, I thought about the same question. And yes, if you can take the discrete log for the easy problem, then you can factor p. Yeah, factoring big primes is one of the big challenges. I forgot who said that, but it's a famous quote. I don't remember, but yeah. Okay, so let's move on. So that's the end of it. So let's move to something else. Yes?
This is similar to the reason to find the quadratic root of prime over a prime is easy, but to find the quadratic root of composite number is as hard as the vector. The vector is hard.
Could be. I'm not entirely sure, but yeah. Yeah. Chinese-Remainder theorem? Yeah, it seems closely related. You can also, another example is why using the RSA numbers, product of two primes. If consider factoring the product of two primes and factoring the product of three primes. If one of the two problems were polynomial time solvable and the other one is not, then guess which one is the hard problem? Factoring three primes, because if I get the product of two, then you multiply it by one more prime, and then you get a reduction. Of course, if both problems are hard and you look into the exact complexity of solving the problems and the complexity of the best algorithms to attack the problems, you are better off with a two prime product, or in this case with a prime modulus. But so let's move on. So this, yes. I'll never get to lattices. Yes.
Do we have any reason to not believe that D-log for all primes of n bit primes, that D-log is hard for all of them simultaneously?
So the if P1 is 1 is smooth, it's easy. Right? If P1 is 1 is smooth, it's easy.
Yeah, no, they are set in there, but so all the known weak cases, in a sense, they have a small probability. So if you pick a random one, I think that you're still pretty safe. But yeah, no, I mean, discrete log is a good problem. I'm not arguing that you should not use discrete log, RSA, or number theory. All I'm saying is that the random self-reducibility does not provide any guidance about the choice of the group. So that's the only statement that I am making, and that's the really remarkable property of ITI's result.
So yeah, but what is the moral of this question? Because you were saying in discrete log you have all kind of sub-problems and it's not clear how they relate to each other, while in lattice problems you have one problem in a way. Mm-hmm. But here you have different problems that do relate to each other. So
like this and that?
Yeah.
But these are different problems. It's not the same problem. So it's so they are. It's not that we are. So if you take each one of them, we don't know how to show that the problem gets harder and harder as you get a bigger modulus.
That goes back to the point number 2, not to this one.
I know, but so this way you get a tower of potentially harder and harder problems. Oh yes, let's use as a problem a discrete log modulo the product of n primes when n is the security parameter, and all these primes have the same size, so that you can actually give this reduction if for these primes. Now, if you do that. Sure, the problems reduce one to the other, but I'm not sure if they really get harder and harder, because I mean, you have these small primes, and so you're not really achieving anything. So it's yeah, you don't really. This reduction does not address the question that I posed in the previous slide.
Without the answer to monotonicity of hardness. I mean, with lattices, you have monotonicity of hardness. You know, the larger the problem, the harder it is.
Yeah.
With discrete log, it's not clear.
Yeah, discrete log is not clear. Yeah, exactly. Okay. Okay, now I know why people refuse to answer this question. Okay. And it's true that I don't have to present any technical work, but I prepared a few more slides. Yeah. Okay. And feel free to ask questions, so I'm justified to go over time at the end. Yes.
Can you tell us about lattices?
Yes, okay, good. Let's move on. So now it looks like I'm not talking about lattice, but I am. Okay, so let's consider another classic problem. This corresponds to the other method to find hard problems. And take an NP hard problem, a famous one, to the subset sum problem. So in subset sum, you are given a sequence of numbers and a target value B, and you want to find a subset of these numbers that add up to B. Now, you can map this problem to a lattice problem. Now, subset sum or knapsack problems are essentially the same as lattices. And the way you map it to a lattice is by replacing each number with a vector and the target also to a vector in a way that finding a subset of the numbers that add up to the value B is equivalent to finding a subset of these vectors whose sum is close to some target value T. And the reduction is pretty simple. This is the reduction. What you do is to extend each of these numbers into a vector with an extra coordinate. And then you extend also the target vector, putting 1, 1, 1, 1 here in these extra coordinates. And it is not hard to see that there is a lattice point in this lattice within distance square root of n from the target, if and only if there is a solution to the subset sum problem. And the details are not important, but the proof is all there. So yeah, you can take a picture or do it as an exercise. Now, so this gives a reduction from subset sum to lattices, but in a sense, we also have a reduction in the other direction. These subset sum or knapsack lattices are in a sense the typical lattice. So it can be, this is a mathematical statement, it's something that can be made precise, and solving problems on lattices or solving subset sum are very closely related problems. And what about knapsack, subset sum cryptosystems? That's something that was already there before Lattice result. That's something that was first proposed about at the same time as RSA by Merkel and Hellman in 1978, that proposed an ad hoc construction that builds subset sum instances and then uses them for public key encryption, and with a conjecture that the crypto system is hard to break because the problem subset sum is NP hard. And of course, if you try to solve it just as a direct general purpose subset sum algorithm, you will fail unless P is equal to NP. And but the system got broken. It got broken because the way they were disguising these structured lattices, knapsacks, into random ones is something that could be recognized. So this was broken by Shamir. Adi, if you're watching right now, happy birthday. And Lagarias and Odlitsko, they gave a general lattice attack that can be thought as a reduction from subset sum to lattice problems. And what these attacks do is to expose the structure of this Merkel-Hellman crypto system, and they, using LLL as a sort of oracle to solve lattice problems, they completely broke that crypto system. Now, you may think that so people kept suggesting other methods to avoid the attack, but they all got broken. And so Lattice result came up at a point when people were finally accepting the idea that, yes, using subset sum, using knapsack, or equivalently lattices for cryptography is just a bad idea, because no matter how hard we try, they get broken. So in this sense, Lattice result was really a turning point for the whole area of cryptography based on subset sum and lattices. So let me get to the description of the function. You already saw some form of this earlier today. So Lattice function is a very simple function. It's essentially a matrix vector multiplication. The key to the function is a random matrix A with elements chosen modulo some small value q. And the input is a short vector x, typically a 0, 1 vector, and the output is just the product, A times x. Now, what I proved is that for an appropriate choice of the parameters, specifically when m is bigger than n log q, which correspond to making the domain of the function bigger than the range, so you get a non-injective function and most likely a surjective one. So for this parameter setting, solving this inversion problem, inverting this function on the average with some positive probability, is at least as hard as solving some lattice problems in the worst case. And you can also see that this problem essentially is a knapsack problem. So there is a knapsack over the group of n-dimensional vectors modulo q. So you can think of it as a reduction between the worst case complexity of lattice problems to a random instance of a lattice or subset sum problem. So that's great, is a great technical result. There is something else that I think was a very important point and contribution of the paper beside proving the result, which is to introduce this class of lattices. It's a very natural class of lattices, but not only is natural, we can prove something about it. And this is still the class of lattices which is used today. For example, the LWE problem, learning with errors, that was used over and over in the morning today, that also can be described as a standard lattice problem, the bounded distance decoding problem, over the same class of lattices put forward by Aitai. And specifically, the lattice corresponding to the function is given by the kernel of the function. When you multiply a vector x by the matrix A, is what in coding theoretic terms is called computing the syndrome of the error x. So it's a specific formulation of the nearest code word or nearest vector problem with respect to this lattice, which is a lattice with some kind of structure. Is what is called the Curie lattice. It's something that we may call Aitai's lattice, where the lattices were put forward and as a good class to be used in cryptography. So these are lattices which are periodic modulo Q. And this allows to use arithmetic modulo Q in any application of these lattices. So you can see the contrast between the worst case and average case problem. So in the worst case, the assumption is that lattice problems are hard. So this is not directly useful in cryptography. First, because it is a worst case assumption. Second, because these are real lattices, and dealing with real numbers is something that requires bounds on the magnitude of the numbers, on the precision of the numbers, and so on. And this is something that is not that convenient, both in practical implementation situations, but even in the theory. So that using real numbers is not too popular. So I don't quite remember who said that. So there are only real numbers in lattices use real numbers, but the only real numbers in computer science are 0 and 1. So usually we don't want to use real numbers. So Aitai's random lattices, these Curie lattices, they use integer coordinates and of bounded precision. And this number Q is also a small modulus. It's not a hard to factor number, not because it is prime. It doesn't have to be prime. The factorization of Q is largely irrelevant in the complexity of the problem. And so the problem of inverting Aitai's function is what this morning was called the SIS, a small integer solution problem. And it gives a way to present and use this problem in a way that does not even mention lattices in the general setting of discrete subgroups of Rn. And connecting these lattices to subset sum even more, it is easy, and it was already remarked in Aitai's paper. You can use a different modulus Qi for every row of your matrix, and then combine them using the Chinese remainder theorem, and that will give you a subset sum problem modulo a single number Q, which is the product of all these numbers. Yeah?
What is the guidance, I'm using your terminology,
yeah.
what is the guidance for choosing Q, like order of 1 will be like some number like 1,000 or something, and then you choose
size. So typically that.
What do you do in practice if you, because there is a number Q which didn't appear before, so just like in the discrete log.
No, you want to use a much smaller number. The security parameter is n, and for all practical purposes, I mean, for the most typical applications, there is no reason to use more than the machine size. Even 16 bits numbers seems to be more than enough.
So you need to use, I guess Q has to be a prime, so...
No, are you asking about how big of a Q or how to choose a Q?
I'm just trying to contrast the discrete log. For discrete log, it's, we can say like the smallest prime bigger than 2 to the n, but that's kind of ad hoc. So,
okay. So I think Russell might have an already answer.
In fact, it actually doesn't matter. Any random instances of subsetsum mod any Q, so you can just pick Q to be a power of 2, and it's actually equivalent to any other Q.
Oh, it doesn't have to be a prime or anything like that?
No, you can reduce it. You can give reductions.
You can just show that for random instances of subsetsum, not worst case, but for random instances of subsetsum, which is what I gets, it actually, the modulus doesn't matter at all.
And most likely even for the worst case setting, because if you can move to the integers just by guessing log n bits. So the carries, when you add up n numbers, they are at most log n bits, so you can guess the carries. So solving subset sum without modulus at all, and solving subset sum modulus something of a given size, they are essentially the same problem. So any modulus reduced to subset sum over the integers in both directions. This is a semi-formal argument. If you want to give an actual proof, you may have to work a little bit on it, but you see why the modulus doesn't really matter.
I guess, but some of the newer papers, especially with adaptive security or complexity leveraging, they use, like, let's say, sub-exponential LWE. So the same argument goes there, because their Q has to be exponential. Well, now it becomes the same as discrete log. No guidance is given in both cases, so...
No, Q only needs to be large enough. So large enough might depend on the application sometimes, but that's it. I mean, the reductions here doesn't really care. It needs to be large enough, and that's it.
You could have exponential hardness here,
yes.
Q is polynomial enough.
Yes.
Okay.
Yeah. Can be polynomial, and usually, so Lattice proof had a large polynomial. In fact, it was for any polynomial time attack, there is a polynomial running time, there is a polynomial Q for which it is hard. And then there was work in improving and lowering this exponent, and the best results are that you can prove hardness for Q as small as n, or even in some settings, even square root of n. So you can make it a very small polynomial. Square root of n, you get very weak cryptographic applications. You get in trouble with, like decryption errors. But that's for correctness. In terms of security, you can, you can prove hardness for Q that is as small as, something between square root of n and n. Bringing Q down to 2, that's an open problem. That's the learning parity with noise problem, so we don't know how to make it as small as a constant, but a fixed polynomial in n is fine, and the factorization of Q is irrelevant. But in a provable way, not just because we don't know how to attack it. So in this sense, we still have a worst case problem. But anyway, so this one is not a worst case side. This one is the average case side of the problem. And for any Q, if you can solve this problem for that Q, then you can solve lattice problems for any lattices where there is not even a modulus. Okay? So you don't have guidance, but you have total freedom to choose your Q within the appropriate range. So, so we see the difference between these two things. And if the, Shamir, Lagaria, Sodlisko attacks could be described as reductions from knapsack to lattice problems, which is something that can even be formalized as a reduction between the bounded distance decoding problem in knapsack lattices to the unique shortest vector problem in lattices. And I mean, this was used before Lattice work. This was used as a method to attack knapsack cryptosystems. And I mean, this paper of Lisko with this title that I think it really says it all: the rise and fall of the knapsack cryptosystem, where he considered many variants that had already been broken, and that seemed to be enough to stop using knapsack for cryptography, but people kept using lattice, knapsack and subsetsum for cryptography, and kept being, beaten up with the LLL stick by Fong, Nguyen, and Jacques Stern, and many others. So just, Fong and Jacques Stern, so they had papers in 97, 98, 99, 2000, 2001, 2005, always breaking, using lattice reduction to break various types of knapsack cryptosystems. So at this point you may say that okay, no, before we get to that. So Aitai in 96, his paper, he could have titled this paper, The Fall and Rise of the Knapsack Cryptosystem, okay? So, I can give a reduction in the other direction, and not only is this kind of a worst case or heuristic reduction, is a very strong reduction, is a worst case to average case reduction. And if you just put aside the assumption that LLL works and as an SVP exact oracle, which in the 80s seemed to be almost the case. The biggest experiments you could run were in a range of parameters where LLL was performing very well. In the 90s, we were starting to get a sense, I was not really doing much in the first half of the 90s, but no, not even that, yeah. And I had a driver's license, though. So at that point we knew that, LLL is not really, SVP is not, the shortest vector problem is not polynomial time solvable. In 98, Aitai also proved that the problem is NP-hard. Before the NP-hardness proof, the conjecture that maybe LLL solves the shortest vector problem in polynomial time was a reasonable conjecture, but at that point you could rule that out. And so if there is some hardness at all, then knapsack is the problem you want to use for cryptography, because it's the problem for which you know how to choose random instances. You don't have to guess and bet on one or another distribution. You trying to ask a question? No? Okay. Okay, so he could have titled this paper "The Fall and Rise of the Knapsack Cryptography," and so at this point you might ask, how come these papers are after Aitai's result, and are people still suggesting knapsack cryptosystems after we know that are still proposing bad cryptosystems once Aitai found how to do it correctly? Well, it turns out that some of these works, they were actually attacking Aitai's function. The first two, 97, 98, is the same paper. One is the preprint version, the other one is the proceeding version. It's exactly the same paper. Slightly different title. The first one is a converse of the Aitai work security proof, which essentially says that, this attack is a reduction in the other direction of what he proved. And for the conference, they chose the more aggressive title, Cryptanalysis of the Aitai work crypto system. And that's how crypto is. It's like gladiators. That's what the 400 people going to crypto want to see. They want to see people going there and then try to kill each other. So just for the sake of the show, but anyway, so the punchline is that so these attacks or reduction, you can always look at them both ways. When you give a reduction, that means that there is a relation between the two problems, and you can think of it as saying, the knapsack problem is easy because it's not harder than the other one, or you can think of it as, we are showing that this proof showing that the knapsack problem is hard is in a sense tight. You can give reductions in both directions, and lattices and knapsack, either they fall at the same time or they stand. And this was kind of clear at that point. And still, this Aitai's function had some shortcomings. And one is that it required m to be bigger than n log q, which corresponded to choosing a non-injective function, typically surjective function, which is enough to get one-way functions You can get commitments, you can get some forms of digital signatures, and a few more things, but getting public key encryption, for example, was a big challenge. It was not clear how to do it out of itide function. And there were some proposals, like the itide work crypto system. In fact, there were two other important papers about at the same time or shortly after itide's work. One is the crypto system of itide and Cynthia here. That it was a theoretical proposal with a worst case, average case reduction. So it had a theoretical support, but it was starting from a different lattice problem. It was a special version of the shortest vector problem called the unique shortest vector problem. You agree? Yeah.
I agree, but the original paper showed equivalence of the unique shortest vector problem with another.
No, only in one direction. Only one direction, showing the unique shortest vector problem is not harder than the general one. And there was a paper much later, like more than a decade later, showing that the unique shortest vector problem turns out to be equivalent to the decision version of the shortest vector problem. So estimating the length of the shortest vector in an arbitrary lattice is equivalent, up to polynomial factors, to finding the shortest vector in when it is unique. But that's something that was not clear at all back then. So anyway, so the other paper is the end-through crypto system, which was in the other class of problems. Based on so mathematical intuition, relation to other mathematical problems, the best known attacks to solve it, and it was efficient. It was really amazing. It was really truly efficient, much better than itide's function, which requires a key size which is quadratic in the security parameter because you have to give out a matrix, and this one had linear or almost linear for the bit size, storage and computation time requirements. So it was very, very efficient, but it didn't have the same kind of theoretical support as itide's function that reassures us that that's a good way to pick random instances. So okay, so to give a sort of, so the state of lattice cryptography at the turn of the millennium, I think that is also well described by an event organized by, was sponsored by N-True. It was the Cryptography and Lattice conference. And it was a great success. I remember going there, it was a lot of fun. I had never seen so many lattice people at the same time at the same conference. And so I really don't know who was there. Maybe, yeah, Jeff, you have the list of people attending the conference, so you can provide a better list. I came up with this list by just looking at the organizers and all the authors of papers presented at the conference, which possibly also includes people that were not at the conference, because maybe of the authors only one went to present the paper. So you see, it's not that big of a list. And if you are familiar with the recent lattice literature, you will also notice that the intersection is not that big. Yeah, there are many names you don't find there, and names that you don't see that often in lattice cryptography anymore. But more than that, if you look at the content of the conference and the papers. So there were about 15 papers in the conference, and of these, 6 were algorithm papers. I tried to classify them based on the titles. 6 of them were like algorithm papers. Another 6 or so were cryptanalysis, and 2 I couldn't quite put them in a clear category, and only one was were applications, but applications not directly related to cryptography. And only one was there is this. So this half paper is there was a invited survey talk by Feng Yan titled "The Two Phases of Lattice in Cryptography," that was describing how lattices can be used both to break and make cryptography, which shows that there was a clear sense that the lattices can be used in both ways, but still essentially there was only one paper trying to do lattice cryptography at that conference. And not even a very good paper. Yeah. I'm kidding. I wrote it. Yeah. Okay. So what can we say? So in the early 2000s, Lattice cryptography was still a very small research community. I mean, these days, if you don't quite have a sense of it, we get more than 100 papers on lattice cryptography every year. I mean, there are so many. If you just search for papers every year that cite either ITI's paper or the RegEv LWE paper as a sort of key to tell whether a paper is about lattice cryptography or not, you will really be, amazed by. I mean, how can people even read? I mean, maybe you don't want to read all of those papers, and even if you want, you cannot. I mean, there's no way to read that many papers, and they're all on lattice cryptography. So there's really no comparison. The community grew enormously. And so at the time there was also still a pretty big gap between the theoretical community dealing with computational complexity, where lattices were primarily a way to connect average case complexity with worst case complexity, which is something very interesting regardless of the practical applicability. And the applicability was also very limited because of the fact that we only knew how to build the one-way functions and little more. And at the same time, we had the more practical community dealing with true encryption schemes and algorithms to break or attack or evaluate the security of crypto systems. And about the same time, there were also devastating attacks to the signature schemes designed along the lines of true that were at the same time part of the lattice cryptography work, but of the kind, let's use lattices to break cryptography. And I think they were also somehow showing the fact that, yeah, this is important, but we don't know how to use it in practice. So we would like to prove things so we avoid this kind of devastating attacks. So the main open problems at the time, I think, were pretty clear. One was to improve the efficiency of ITI's function, or maybe even improve the security of true. And the true encryption is still is a good encryption scheme. And in fact, today we have a better understanding of how it relates to other provable lattice cryptography and why the signature schemes got broken and while the encryption turned out to be a good one. So this efficiency was one of the big open problems. The other one was to prove security of the injective version of SIS. Of SIS, which seemed to be the key to design more powerful applications like public key encryption. And this is something that also relates to knapsack. In the algorithmic attacks to knapsacks, typically you distinguish two settings, the low-density knapsacks and the high-density knapsacks. High-density knapsacks correspond to hash functions, and low-density knapsacks come up in public key encryption, and low-density knapsacks are those for which lattice attacks were most effective, those that got broken. So getting security for low-density knapsacks or injective versions of ITI's function was another big challenge. And something else that I think was beyond anybody's dream, if anybody in the room can correct me, please do, is that, at the time, pairing-based cryptography was all the rage. That was a cool area of cryptography, while there were a bunch of small community of people working in lattices, but that was where the cool kids were playing. And so the idea that lattice cryptography could match or even surpass pairing-based cryptography in efficiency, versatility, and popularity was something that really could have been a joke at the time. So you wanted to say something in the back?
So the big open problem, are they still open like after 15 years?
Are you asking if they are still open today? Yeah. No, I'm going to move to that now. So that's what I will be talking about in these last 30 minutes. Okay. And so as we get closer and closer to today, since this is a historical talk, I will say less and less. But you already saw some of these things earlier this morning. So yeah, I'll try to compress everything in time a little bit, over time. Yeah, it's less than 2/3. But I told you, we'll ask questions, so I feel justified to go over time. So let's start with efficiency, one of the two open problems. So this problem, so a first blow to this problem came in a paper of mine, Generalized Compact Knapsacks and Efficient One-Way Functions, blah, blah, blah. I think it's a bit longer than that, the title. So what the paper did was to consider a structured version of Lattice function. So the source of inefficiency in Lattice function is that you have a two-dimensional object, a matrix which has n² storage requirement. So if you build a matrix that is structured, you can think of it as a matrix divided into blocks where every block is a circulant matrix, a matrix where every row is a rotation of the previous one. So you can implicitly represent this matrix, this square matrix, with just a vector. So if you do that, you get a matrix with linear or quasi-linear storage requirements. And using FFT and polynomial arithmetic algorithms, you can even compute this function in quasi-linear time. So you can get a fast function, a function that matches n true in speed, by and large. But not only that. What this paper showed is that you can still prove security. You can get a sort of scaled-down version of Lattice result. So if Lattice showed that if you can break this random problem for random, uniformly random matrices, then you can solve lattice problems in the worst case. So what I showed here is that if you can break this random problem for a random circulant matrix, then you can solve lattice problems in the worst case over a class of lattices that has a similar restriction, namely the class of cyclic lattices. Lattices that are closed under a cyclic rotation of the coordinates. So, I mean, the assumption is definitely stronger than Lattice, so because but it's still worst case. We are considering a worst case assumption over a restricted but still natural class of lattices. So if we believe that lattice problems are hard to solve in the worst case over cyclic lattices, then we know how to build hard random instances.
Daniele, when you do the worst case or edge case reduction, does the dimension of the lattice get much bigger?
By a log n factor. Yeah, it's just a log n. In fact, it can even be a constant factor. If the input is a 0-1 vector, then you need the log n blocks to make the function surjective. If the input are small values that are at most q to the epsilon, then you get a 1 over epsilon blow up in size. So you can make it constant if you want. Okay, so there are a few differences. One of them is that while before I showed you that for general lattices, we know that if you increase the dimension, essentially you're taking a harder problem because you can add more coordinates. So that reduction does not preserve cyclicity. So it's not clear how to reduce hard problems on cyclic lattices in dimension n to cyclic lattices in dimension n plus 1. And but what does this say? So this says that the proof tells us how to choose random problems for Cn, for every n. It doesn't tell us how to choose n, how to choose the security parameter. So,
it's always true.
No, in Lattice case, you can reduce lattice in dimension n to lattice in dimension n minus 1. It's not entirely correct because the approximation factor also grows in with the dimension, but if you leave that aside, you can embed.
One of the weaknesses of what we do is that we don't get good guidance for the security.
But okay, so we don't know how, in a absolute sense, we don't know how big should it be. But at least we know that the bigger the better. So here, it could be the case that solving lattice problems in cyclic lattices is polynomial time solvable if the dimension is even, and exponentially hard if the dimension is odd. That would be quite surprising to me. But it's not something that we can rule out with the strength of mathematical proofs. So that's what I meant. It doesn't provide guidance. But that's a much weaker issue. Still, for every n, we do have a hardness. Plus, I think it should be possible using some kind of padding argument to get a sequence of problems that get harder and harder. For example, you could define the problem in dimension n to be solve lattice problems for cyclic lattices in dimension 1, 2, 3, 4, 5 up to n. And if you consider such a sequence of problems, then it clearly gets harder and harder, and you can reduce it. But of course, you also lose all the efficiency advantages, so little point in doing that. So, also we could only do one-way functions. Yes.
So it wouldn't be so surprising if it were easier for some n's, because doesn't it have a lot, and you're probably going to get to this in a minute, have a lot to do with the factorization of x, the polynomial x to the n minus 1?
It does. It's going to come up soon. It comes up in the context of finding collisions to these functions. But when it comes to inversion, the factorization somehow doesn't play a that big of a role. So, in fact, for Lattice function, at least we could show that it is a one-way function, it is a collision-resistant hash function, and there are a few related applications like commitments and so on. For this one, surprisingly, I could prove one-wayness, but I couldn't prove these other stronger properties. And I left it as an open problem. This was in 2002. Either find collisions or prove that it is also collision resistant. But for some technical reason, the proof was breaking up there. Yes?
You don't know how it helps here, right? But it could.
It could. No, but the one-wayness proof works for every n. I mean, there is the worst case side and the average case side, so fine. Maybe I should take back what I said, but yeah, it could. Okay. But anyway, so moving on, so I think an important point that was sort of not quite understood at the time, that so this proof was not really just a scaled-down version of Lattice function. I think that was kind of the impression that people had. My paper got rejected when I submitted to a journal. I mean, the conference was fine. I sent it to Fox. That's fine. It's just a conference. Then I sent it to a journal, and then after more than a year of reviewing, I got back in one-liner saying that oh no, we don't. Yeah, it's not good enough. Actually, the concern of the reviewer was that, hey, this paper is using a new assumption, and what if the assumption gets broken? That would ruin the reputation of the journal. And if you think about the kind of assumptions that we've been making in these last few years to get multilinear maps and obfuscation and so on, what?
That's why we don't send it to a journal.
Yeah. So it's. I was trying to support the journals by sending my best work there, and yeah. No, but anyway, I think so. I mentioned this. I mean, not just to bash on the journals. Was to. So I think this kind of this was representative of a general. Sentiment within the lattice cryptography community that these cyclic things are not that interesting. Come on, we already had and true that we can use it, and this one is not practical anyway. You cannot use it. But it was the starting point for a very nice connection between lattice cryptography and algebraic number theory. So. It took 4 years before somebody else came up with the result along those lines. And the two papers, they essentially proved the same result. So I remember when I first saw the first paper by Chris, Packard, and Alon Rosen, that I didn't know whether to be happy or mad. I mean, you see, so you have a new result, and then you see another paper with the same result. Oh, you got spoofed, and they already sent it to a conference, and then we sent our paper to the first conference deadline around the corner, and our paper got rejected for unclear reasons. And but still, there are two people. I mean, Vadim Lubashensky didn't really count as one more people working on lattices because at the time he was my student. So yeah, it was not an independent. It didn't show independent interest in these cyclic lattices. But still, you know, even if they got the same result, I'm not alone. There are two more people working on these cyclic lattices. That's great. That's three. And
if only they would have worked on it a few months later. If only they had worked on it a few months later.
The paper were not identical. In fact, I think there are interesting things. So let me tell you what the two papers did. Was to show that my one-way function is not collision resistant. You can break it. You can find collisions. And then they suggested to do two different ways to fix the function and make it collision resistant. And the way you do it shows why the factorization of n is important. And Chris and Alon, what they did was to work modulo a prime, while our paper worked modulo a power of 2, and so they were both interesting solutions. And let me just give you another small test. And so this one is an instance of my one-way function. Okay, so each block is a circular matrix. You see the rows are cyclic rotations. And how you compute this function, you multiply it by 0, 1, and minus 1, and take the sum of these columns, and you get the output. All the arithmetic is modulo 10, so you only have to do single-digit arithmetic. And you want to find a collision. So a collision means two subsets that have the same sum, or equivalently, you can take one subset and multiply it by 1, the other subset multiplied by minus 1, and you want to get 0 as the sum. So the question is, can you find a collision to this function? You have 10 seconds.
Yes.
Yeah?
Yes.
Yeah. Right answer, yes. Prove it. So, no, yeah, it's easy to find it. So there was a similar hash function that was presented at a ramp session of Crypto the same year. That was essentially the compression function was my one-way function, and they suggested using it for compression. And yeah, so they got a hash function there, and then I remember Chris writing a small program, I don't even know in what language, during the break between one session and the other, and then submitting one more ramp session titled Talk, and presenting our lunchtime attack, because we worked it out during lunch, and we had a collision. So, but anyway, so the way we could do it so easily is, why we could do it is more interesting than the fact that it could be attacked. So proceed as follows. First, you multiply everything by 1. Now, since these matrices are circulant, when you multiply them by 1, you get a constant vector. And once you have the 4 constant vectors, then finding a collision is easy. You know, 6 plus 3 is equal to 9. And you found your collision. And now this method to attack the function is directly related to the factorization of the polynomial x to the n minus 1. Now, working with circular matrices, in polynomial terms, can be described as working with polynomials modulo x to the n minus 1, so that when you get to position n, you go back to position 1. And this polynomial factors into a linear factor and something else. And this one-dimensional problem corresponded to moving to this, projecting onto this linear factor. So that's where the factorization comes up. Now, let's modify this a little bit. So it's the same matrix as before, but I'm changing the sign of these entries. So these are what is called, or could be called, anti-circular matrices, which are matrices where when you rotate your row, the entry that goes around gets negated. Okay? So this seems just a trick to avoid the previous attack. Now, can you find an attack now? You can still easily write a little program and find the collision just by brute force. But coming up with a structural attack is much harder. I mean, I don't know any structural attack to this. And in fact, let's skip this triviality. So the version of the security proof given in my paper with Vadim showed that this problem with this tweak is as hard as the worst case complexity of lattice problems on anti-cyclic, anti-circulant lattices. So there is a worst case to average case connection showing that you cannot find collisions to this. And this is related to the fact that the polynomial x to the n plus 1, which corresponds to negating the entry that goes around, is irreducible over the integers when n is a power of 2. So, okay, so there is a lot of work that was done since then, getting more and more algebra into the study of efficient lattice cryptography. But I don't have time to talk about that. I want to say a few more words about the other problem, the one of getting more applications rather than just one-way functions. And so for that it is interesting to think of this SIS I-type function problem in geometric terms as a lattice problem. Now we have seen that multiplying x by a is like computing the syndrome of x and is some version of the closest vector problem. So if this is the Curie lattice and then you get a vector x, the operation of computing the function can be equivalently described as taking your error vector and reducing it modulo the lattice. Think of it as sliced, cutting your lattice space into parallelograms and then putting all of them one on top of the other. So this is the function computed by I-type, reducing the error modulo the lattice. Now, at this point, you can ask, is this function hard and for what values of the parameters? Now, when the size of the error is less than half the minimum distance of the lattice, this function is injective. So all these fragments of a ball do not intersect, even when you reduce it modulo the lattice. Now, if you choose a larger error, at some point they start intersecting. The function is not injective anymore. And if you make it big enough, then the function will become surjective. It will cover the entire space. And you don't need to make it that much bigger to get something which is not only surjective, it is also regular. So notice here, different regions have different shades of red or pink, I'm not sure. So I often get into, discussions about whether the difference between red and pink. The discussion is typically about the color of my shirt, but yeah, it's. It is light red. It is light red. The LaTeX command that I used was red, and then I use only 50% or 70%. So here, when you make it bigger, you still have different shades, but the difference is much less. And so you get something that is almost regular. Every point has roughly the same number of pre-images, and this function maps to the uniform distribution. And so you can ask, so is this a one-way function, and in what range of parameters? And I-types show that in this case, when the function is surjective and uniform, then the function is hard to invert. And the question that was the key to designing public key encryption schemes based on lattices was, can you show that this function is injective, is hard to invert, even in the injective range of parameters? And that's the question that was answered, perhaps implicitly, by Oded Regev in his paper on lattices, learning with errors, random linear codes, and cryptography. And I said implicitly because this was proved not using the SIS problem. In fact, I'm not even sure it was clear to him that the problem was, what he was doing was to prove the hardness of I-type function, but for injective values of the parameters. He was formulating, proposing a new formulation of the problem called learning with errors. And but yeah, just using lattice duality, it's easy to show that there are different formulations of the same problem. So, and not only that, but and the way he did that was even more surprising. He could prove that the function was hard to invert in the injective setting using quantum computation. So that's why it seems so out of reach before. And still today we don't quite know how to relate these two problems using classical tools. So technically use the quantum Fourier transform to move from one lattice to its dual. So beside that, perhaps less surprisingly, he also showed that if this function is one way, which he showed, then it is also pseudo-random, in the sense that the output of the function is indistinguishable from a uniformly random value. I said less surprisingly because if you formulate it in the SIS version, so like a knapsack version, there were already results by Russell in Pagliazzo and Molinaro showing that the subsetsum problem, if it is one way, then it is pseudo-random. That's something that we already knew using this formulation. Perhaps it was less clear when using the other one. And finally, it could be used for public key encryption. So he gave this application, which was great, because at the time, it was an application based on the worst-case assumption of the quantum hardness of lattice problems, but he could get public key encryption, a serious and useful application that you can potentially sell and make a lot of money out of it. So, okay, so you already saw this in the morning many times, so yeah, I'll just skip it. So so syntactically it looks different from the previous SIS function because of this addition here, but indeed you can rephrase it by taking the dual of A, the orthogonal complement of A, and then use it as a parity check for E, and you get an equivalent function that is syntactically similar to ITI, but for different parameters. Now, LWE really had a huge impact in cryptography. After starting with 2008, we started seeing more and more complex applications, from lossy trapdoor functions and CCA secure encryption, identity-based encryption, hierarchical and so on, oblivious transfer, all the way to fully homomorphic encryption. And something that I heard many times since then was that, oh, you know what is really the great thing about this LWE problem and this paper of Regev? So he introduced this problem that allows you to do lattice cryptography without even knowing what a lattice is. Okay? And I mean, each time I hear that, I really don't know what. I feel like crying almost, okay? Because no, I mean, he did. Oh, sure. I mean, he introduced a new problem, but honestly, I think that's almost a negative contribution, because that, confused everybody, because they couldn't see that, oh yeah, that's the injective version of ITI's function. Oh no, that's something totally different. And but at the same time, what he did was to prove that that function was one way, something that was a big open problem. And we compared it to the introduction of a different syntactical formulation. I mean, that's a much bigger achievement. That was really, really surprising if you look at it from a lattice perspective. But anyway, I think that to be fair, if there are 100 papers a year on lattice cryptography now, I think it's also because of the fact that yes, you can do lattice cryptography without even knowing what a lattice is. Now, I think you can do that equally well using the SIS formulation. It's not something that, this is something that is often attributed to the LWE formulation, but most of these applications you can work them around and use the ITI's function, but for a range of parameters that were proved secure only by Regev. So that without that, it would be just bad to use those functions. Yes? Mm-hmm. So depend on which problem you start from. So there have been classic reductions showing hardness also for this function. So the difference is that ITI proved that the problem was as hard as finding n short linearly independent vectors in a lattice in the worst case. So the classic reductions only show you that it is as hard as computing the length of the shortest vector in the lattice, but without finding it. So it is still very interesting, and it was so this was achieved first by Chris Peikert, and proving a sort of classic hardness for this problem, starting from gap SVP, is something that you could think of it as a dequantized version of ODED proof, but it's not really dequantized, meaning that the part where quantum was used is still there. We don't know how to make that part classical, but still that reinforces our confidence in the problem. But at the same time, so this kind of proofs, they do not carry over to the algebraic setting. Okay? So there are open problems related to it. It's an area that is not completely solved. And and there is one more paper that I should mention, from last 2 years ago, that I'm blanking out. But yeah, there are 4 people in the room that they know what I'm talking about, and please, if you want to hear that, please, raise your hand. And but anyway, so I'm trying to close, to get to the end of the talk here. That was the opposite of what we had before. It's something that is as inefficient as Lattice function. So it is practically useful, but only theoretically efficient. And so this is a sort of background slide. So this is C code. It's MD5. No, it is not. It's a lattice crypto function. This is just a hash function. So at the time, getting something that was practically useful was still a big challenge. And but in the case of hash functions, in 2008, we managed to find a truly practical implementation of those functions. It's something that could really go as fast as you want. It was a hash function as fast as SHA-2 using various implementation tricks, and that was probably the first work that showed that yes, you can make this lattice cryptography using cyclic lattices really efficient. So unsurprisingly, I wrote a little program to find the best parameters, and the answer turned out to be 42. So if so we didn't know to what question that was the answer before. So this paper answers the question, what is the question to the 42 answer? And but anyway, so let's move on. So if you try to put these sort of foundational papers in a table, we have the surjective and injective versions of this SIS function, and we have the less efficient and more efficient version depending on whether you use structured lattices or not. And ITI founded this whole area giving a surjective function based on general lattices. Regev got the efficient, more powerful injective version that has tons of applications but still inefficient. Then the cyclic lattice work got efficiency but only here. So you can ask, okay, we should put something there. And that was done by Lupaczenski, Peckert, and Rosen, and Regev in 2010, giving basically combining these two things. Technically, they had to do much more than that, and proving pseudo-randomness of this function was something that brought even more algebraic number theory into the game. So there are several other related papers that technically they are equally important, and one of them that I like to mention is a paper in 2009 that it predates this one by a little bit. I think that technically the results are independent by Damien Stelle and others, that it showed that this function was one way, but without showing pseudo-randomness. Technically, it's very, very interesting and nice. I really like that proof, but proving pseudo-randomness, in a sense, is really the what was needed to get the fast and powerful applications. And so let me close with FHE, fully homomorphic encryption, which I mentioned in the title, but I'm not going to say a lot about it because you know, it's, I mean, it's already history. I mean, it's Craig result, but you heard about it in the morning. And so Craig Gentry in 2009 did something really amazing. And I think that even more than solving the problem, what he did was to convince people that the problem could be solved. And similarly to what ITAI did in, you know, taking this knapsack problem that everybody was throwing away and say, oh, no, this is something that is completely different. You can do it. Same thing. FHE, yes, all of a sudden everybody in cryptography started thinking that, oh, yes, it can be solved. And it also brought a lot of attention and publicity to lattice cryptography, which is good, so nobody complained about it. But now, after some time, I think that we can finally say that, oh, perhaps for the wrong reason, okay? So, and the wrong reason is that the way he was using lattices was very different from ITAI. He was not using that class of lattices. He was using a lot of ad hoc assumptions, which it's not as clear how confident we can be about them. And related to that, there were also some efficiency issues. So there were several papers after that got second generation, third generation. I don't know up to what generation we got at this point of better ways to do fully homomorphic encryption, based on problems which now are essentially LWE, the same boundary distance decoding on ITAI's lattices. So why I said perhaps for the wrong reasons? Because Gentry used the ring lattices, these algebraic lattices, and so in that paper it seemed essential to get a fully homomorphic encryption. You want lattices that support both addition and multiplication in order to get a complete set of Boolean gates. And but it turned out that that's not really necessary. So that's useful for efficiency, but not quite the case. It was using a different class of lattices. The really key feature that was important, that is still present in all these newer FHE scheme, is that lattice cryptography has a very fast decryption algorithm. That's really something that is unique to lattice cryptography. Decryption essentially is a scalar product. You saw this morning also in Hotek's talk. And if we look at FHE today, it's quite different. So in fact, I mean, it's quite different to the first candidate proposal. FHE encryption today is essentially reg LWE encryption or variants of it. And the security is based on standard assumptions, LWE or worst case hardness assumptions on lattices. There is no need of ring lattices except for efficiency, and it is also much faster and well understood than the first candidate. So a few concluding remarks. ITAI's connection, sure, is not as powerful as LWE. We cannot do fully homomorphic encryption just using that, but the impact of that work on lattice cryptography is something that we can still see today. So you can think of this class of Curie lattices that was brought to the cryptographers' attentions in that work, and we still use them today with great success. And the theory behind the proof really put lattice cryptographers on the right track to get both faster functions and better understanding of what they are doing. And of course, I only mentioned, also going back to Shafi, I only mentioned a small fraction of all the works that I should have, that deserved to be mentioned. That was because of timing constraints. And there is clearly still plenty of work to be done on many fronts, from getting better understanding of these algebraic lattices to implementations. Implementation of lattice cryptography is not about coding, it's about mathematics. So what makes these things efficiently to implement is the choice of parameters that allows you to exploit structured algorithms like FFT algorithms, number theoretic transform, and so on. And there is a great potential for parallelizability and hardware computation, because you're working with vectors, and I think sooner or later we'll have, the newest generation processors with instructions to support lattice cryptography. So that's something that, back 20 years ago, at the time of, 1996, that would have been, we already had that. That was only used in addition, and yes, addition is well supported by computers. But maybe, we'll go beyond that. And for all this recent work on obfuscation, multilinear maps, and so on, basing those functions on standard lattice problems, I think is really the key to move forward, both in terms of efficiency and also really do something like real cryptographers alone would say. Real cryptographers don't use obfuscation. So, with the confidence that we know what we are doing when using lattices. And security estimate, yes. So getting concrete values of security for lattice cryptography also is something that I think requires more attention. And the reason is that most of the algorithmic work that was done before and after ITI's work was to a large extent done in the context of breaking things. Now, when you break things, you are in a different kind of setting than when you are trying to estimate parameters. If you want to break a scheme, you just try to attack a challenge, you break it, fine, and the scheme is dead. So if you want to get confidence of how much it would cost to break something, you need some more algorithmic and statistical study of the problem that is not focused on a single instance, but tries to improve our understanding of the performance of the algorithms. So revisiting many of the algorithmic problems on lattices, I think, could help in that direction. So that concludes my talk. So thank you all for your attention.
Questions or the chat? So to summarize, there is no FHE, so it's an open problem. You get an FHE that's based on a search problem related to lattices, so on finding rather than estimating the size. Even with the quantum proof.
No, quantum proof, yes. With the quantum proof, yeah. In fact, the quantum proof, you can describe the quantum proof as a reduction between the search problem to the decision problem. So in one direction there is a classical proof, just as a complexity question. Can we relate the complexity of search as IVP with the complexity of gap SVP? So there is one trivial classical reduction in one direction. In the other direction we only have quantum reductions. That in the worst case setting, that's what was done in Oded's paper. In the average case setting, that's what was done by Daniele in the SSTX paper, where they did something like that, going between average case problems, but that's only quantum, but it gives hardness based on a search problem.
So for search, what do you need? One-way functions, collision resistance?
Classically or quantumly? Quantumly is the same, yeah.
One-way functions, collision resistant? What else?
Digital signatures? No, but you can do it directly. You can do efficient signatures. No, then yeah, I think that's it pretty much. There are all the problems that can be reduced to one-way functions, commitments, I mean the kind of, that you can do from one. Yeah, collision resistance is the only one for which we have no reduction, but everything else is polynomial time equivalent to one-way functions.
And those characters, they see that this is a big, huge difference between the two. Search versus decision.
Yes, I mean, the best way that we know to estimate the length of the shortest vector is by finding it. We don't have, except in the algebraic setting, but in the classical setting, I'm not sure if algorithmically there is anything that can be exploited. But the search version, the decision version is polynomially equivalent to the unique shortest vector problem, which is considered easier in cryptanalysis. But if you apply the reduction, then what you gain that way, you lose it in the reduction, so it's not clear if that's a good way to estimate the length of the shortest vector. Yeah. There was a question in the back? Yeah.
Different question. So you said introducing LWE was a disservice to
No, it was good because I think it brought so many people to the field for the wrong reason, but I mean, it's still good, so I'm happy about it. Same thing, all the publicity from, the FHE and so, great, I mean, yeah.
So it used to be the case that when you think about sort of lattice crypto stuff, right, or one-way functions, collision resistance, there's a natural geometric way to think about it, right? So that, in fact, my former advisor used to ask me every time, or something, what is the geometric way of looking at it? Do you still think that's with FHE, for instance, there is still a natural geometric way to look at these themes? Is that the right way to think about it, or should we just collapse back to algebra?
So first, also my advisor told me the same thing. And yes, so some of the things you were showing this morning, and then, okay, this looks like a trick, just matrix manipulation, you multiply things only because the dimension matches, and things work out, great. And you can check that it's correct. I believe that there should be some kind of geometric interpretation, and even if you don't need it to carry out the proof, it can be interesting, and there is something to learn from trying to do that. It might give ideas to do other things, more things, or even getting a better understanding of what we are doing. So, yeah, I'm a true believer in geometry, in the geometric view of lattice cryptography.
Okay, so I think we'll go outside to the reception. It's outside here, and we will see you all tomorrow morning. And let's thank Daniele again.